Staying with this graphing concept for visually proving some things, let's take a look at another type of function pairing, which is called a cofunction. So co stands for complementary. Sine and cosine are complementary functions of one another. Tangent and cotangent are complementary functions of one another. And secant and cosecant are complementary functions. If I were to redefine this chapter of mathematics, I likely would have taught everybody sine, secant, and tangent, so that way we could then examine our complementary functions. And perhaps that might even be more useful to have your calculators have a sine, secant, and tangent button rather than sine, cosine, and tangent buttons. But generations of habit, I suppose, leads us to where we are. So here's an example of a graph of cosine, and I'm going to draw another example of a graph of sine. Now, you can see that these graphs are equivalent, and I don't mean exact, I mean they're equivalent. One can be mapped to the other. I can take the red graph and I can translate it over so that it lands on the purple graph. And to do that, all I have to do is translate this maximum or this extremum pi by 2 units to the right. So I can take cosine and I can move it pi by 2 units to the right. Now, how do I move something pi by 2 units to the right? Well, this goes back to the transformations that you would have learned in grade 11. To move something pi by 2 units to the right, I'm just going to go subtract pi by 2. And you'll now see that my red graph has moved directly over top of my purple graph. So there's the purple graph, sine of x, and there's the red graph, cosine of x minus pi by 2. So this is a cofunction identity. Cosine of x minus pi by 2 is equal to sine of x. Now, I don't particularly like this cofunction identity. I prefer this written in a different way. I prefer it written in the way this. And it gets the same effect. So my red graph lines up over top of my purple graph. But notice there's something really different there with the signs. Not sine, S-I-N-E, but sine, S-I-G-N's. I've moved the negative pi by 2 term over and taken out its negative sign. And I've moved the x sign over and taken out one of its negative signs. I know it previously had been a positive term, so removing a negative makes it negative. Now that negative was really just common factored. So essentially, I common factored it to the front. But awkwardly enough, nothing happens. You may remember the reason why nothing happens is because cosine itself is an even function. So if you have a negative in front of all of these terms dealing with x, remember in translations, negatives in the input cause reflections about the y-axis. Well, even functions are already reflected about the y-axis. So we can write our cofunction identity in this manner, pi by 2 minus x. And I particularly like that because it's rather easy to remember. Complementary angles are angles that add up to pi by 2, or 90 degrees. So if one of the angles is 40, the other angle is 50. If one of the angles is 70, the other angle is 20. If one of the angles is pi by 6, the other angle is pi by 3. We know that whatever one angle is, to find the other one, we just subtract it from pi by 2. Now, the reason why I like this structure better is because now it doesn't matter which function I write in place. Check this out. Let's take cotangent. So cotangent's a particularly weird graph, but cotangent is complementary with tangent. So cotangent of pi by 2 minus x should and does equal tangent of x. And I can just reverse those. Tangent of pi by 2 minus x is equal to cotangent of x. I can do this with any of my identities, so secant and cosecant. All of my functions that have that co are related in this way. Now, let's take a quick look back at tangent and cotangent and why I preferred writing my expressions like pi by 2 minus x. Originally, we had taken x and subtracted pi by 2. Something's up here. The reason why something's up is because tangent isn't an even function. This would work for other functions that have even relationships. Like, for example, if I took secant and cosecant, this works because secant is an even function. But if I change the order here, cosecant and secant, it doesn't work. So I preferred that order of pi by 2 minus x because it goes back to the definition of co representing complementary. And to find complementary angles, we know the sum of them, pi by 2 minus x plus x, has to equal pi by 2. And pi by 2 minus x plus x is always going to be equal to pi by 2. Because the x's would just simply cancel. So those are some cofunction identities. Now there's lots more of them. Let's go back and take a look at the sine and cosine ones. Another interesting sine and cosine one is pi by 2 plus x. Now that works for sine, but it doesn't work for cosine. And again, that happens because of the odd-even functions, but it also happens because of the cast rule. So if you think about what happens with sine of pi by 2 plus x, well, sine of x, purple graph, gets moved back to become cosine. Whereas if we did this the other way around, with cosine of x and cosine of x, our cosine would have gotten moved back, but it wouldn't become sine now because sine starts at the origin and goes up. Instead, it would become negative sine. And that's because of the fact that sine is an odd function. So there's lots of really interesting cofunction identities, but I find that the easiest ones to remember are simply the ones where you have a function or a cofunction, and the angle or argument is pi by 2 minus x. That's going to be equal to whatever cofunction you have of just x. So those are some representations for cofunction identities and why they work.